today I was asked to do a more general talk. So rather than talking specific about research, like recent research I've done, do a more big overview of a problem. So of course, I'm going to do an overview of Erdős Ko-Rado type theorems. As I started doing this, I realized that there's just so much and so many different perspectives. It just got longer and longer. So I hope I don't go too over time. But what I tried to do is add lots of references so you can go back and find the different areas and what people are doing. And I kept adding more and more references, and I've missed so many people and so much work. So I apologize for everybody who I should have references to their work, but I don't. Oops. Sure, sorry. I tried to move things and I closed it. Okay. Okay, that looks good. Okay, good. And just before I actually get started, I can see the chat and I can see your faces. If you have questions, you can just turn on your mic and ask, or you can put it in the chat and I should be able to see it. Okay, so let's start right here. I want to do it like this. Perfect. So I have a couple references. I've got the original paper. So the original paper, Intersection Theorems for Sets of Finite Systems, came out in 1961 by Erdős Ko-Rado. The lore behind the Erdős Ko-Rado theorem is that the original proof was done sometime in the 30s, but they didn't publish it until later, until the 60s. And when it came out, there's like all these papers that came rapidly afterwards doing different variations and simpler proofs of the theorem. In terms of more modern references, David Ellis put a paper on the archive quite recently that's a lovely overview of intersection problems in extremal combinatorics. And it's a really nicely written paper, and it covers all sorts of different related problems. And there's also a book that Chris and I wrote, Erdős Ko-Rado Theorems. Our book is mostly about algebraic approaches to the EKR theorem. Yeah, it's a whole big book. So let's start with what the actual theorem's about. The theorem is about set systems. So I have an example here. I have an intersecting three-set system from 1 to 7. So 1 to 7 is my base set. It's where I'm pulling numbers from. A 3 set is the size of the set, 3 elements, and any 2 are going to be intersecting. And so what I have right here is an intersecting 3-set system. And if you look at it, you see 1, 2, 3, 1, 3, 2, 3, 2, 3. I've picked this set system so that every set has at least 2 elements from 1, 2, 3. So I have a set of 3 elements. All of my sets have at least 2 of them, so they're going to have to be intersecting. And I've got 9, 10, 11, 12, 13 sets. But I can do better if I take this set system where everybody has 1. Now, if everybody has 1, for sure, it's going to be intersecting. The size will be all the numbers but 1. Fill them in every spot but 1. And in this case, I get what, 15? And so I can make a bigger set system. The second type of set system, where I've got a common element in everybody, he's got a bunch of different names. In the older literature, it's called trivially intersecting, which you could see how that could be confusing. Sometimes it's called a dictatorship because 1 is ruling everything. Some people call them a point pencil. I never know if they call it a point pencil or a pencil point, but I have to say that term has never made any sense to me. And somebody once drew pencils with points and said it's just like that. And I'm like, okay. I prefer the term canonically intersecting because it's intersecting in the most obvious and simple way possible. So by canonically intersecting, I mean the collection of all the thingies that are intersecting because they all have a common element. Okay, so the question when we're looking at the EKR theorem is, what's the largest set? What is the largest intersecting set system is the big question. And there's a bunch of sub-questions embedded in this. One is, what's the size? And the second question is the canonical one, the easiest system to make, is that the biggest? And then the second question is about the structure. And is the largest system always a canonical one? So it could be that the canonicals are biggest, but there's another system That's not canonical, that's the same size. And we also talk about T-intersecting. The examples I showed before, the sets always have at least one element in common. We could ask for having at least T elements in common. So with the Erdős Ko-Rado theorem, what we have is we're looking at a T-intersecting K set system on an N set. So we're starting with N numbers. We're picking K subsets. And what we want is if we take any two subsets, their intersection has to have size at least T. And now there's this little comment here. If our N is big relative to the K and the T, then the largest has this size, which is the size of a canonical one. So where I take a fixed T set and I take all the K sets that contain it. And the only time we have this bound is if it's canonically T-intersecting, so that easiest to make system. So this was the theorem as it came out in the 60s. Erdős Ko-Rado had this bound. They said the lower bound on your K and T is some number. It's going to be K choose T cubed, a bunch of other stuff. And they were like, yeah, this bound, you need something. We don't think it's right. And so Frankel jumped in and he proved the correct bound. But his proof was sort of wacky in that you needed your T to be large. I think your T had to be like 14 or something. And Wilson came in the 80s and did a lovely algebraic proof that gave the exact bound for all T. And then in the late 90s, Alsveda and Ketch-Tryan had a beautiful paper where they gave the largest intersecting sets for all value of N, K, and T. So they've got the exact formula. Like if you take their theorem and you give it an N, K, and T, their theorem will tell you what's the size of the largest and exactly how to build them. So we can ask the same question. So what's the largest set of intersecting things for a whole big bunch of different types of objects? So the original EKR theorem had to do with sets, and two sets are intersecting if they have a common element. We can look at blocks in a design, and then intersection's pretty clear. We can look at multi-sets and say two multi-sets are intersecting if they have a common element. We can look at vector spaces over a field, and we get to find intersection by the dimension of the intersection. We can look at lines in a partial geometry. We can look at integer sequences, and then integer sequences, if they have the same entry in the same position, you can call that intersecting. We can look at permutations, and there's more than one way to think about permutations being intersecting. So you could see permutations as mapping i's to j. So if they both map a common I to this common j, then they're intersecting. Or maybe they have a common cycle. Like if you take your permutation and write it in a cycle structure, they're intersecting if they have a common cycle. We can do set partitions, tilings. Say we take a chessboard and we take 2x1 domino tilings and lay them down. When are they? They're intersecting if you have a tile in the same orientation in the same position. We can look at co-cliques in a graph. We can look at, take a vertex set and take two distinct graphs on that vertex set, and then look at their H intersecting if they both have a subgraph, H as a subgraph. And we can also look at triangulations of a polygon. And so for all of these things, we can ask, what's the largest set of intersecting objects? And we can ask for the size, and we can ask for the structure. So we can turn this into a fairly general framework. If we think about objects being made up of atoms. So two objects are going to intersect if they contain a common atom. So sets, your atoms are elements. Integer sequences, your atoms would be pairs, that would be position and entry. For permutations, we could define them as pairs, I goes to j, or we could write our permutations as disjoint cycles, and each atom is a cycle, and we can put disjoint ones together to make a permutation. So with this framework, we've got this natural idea of a canonically intersecting set. A canonically intersecting set would be all the objects that contain some fixed atom. And then we say that the objects have the EKR property if the canonical intersecting set of objects is the largest. So where we have the size. And we can say they have the strict EKR property if not only are the canonical ones the largest, but they're the only sets that are the largest. And so now we've got a pretty general framework to talk about EKR theorems. Anytime you can set something up like this, you can start asking for EKR type results. There's another general framework. This is a lattice. And what I can do is, holding on to a lattice, I say that two objects are intersecting. So say I take this element and this one, and I can trace down and hopefully find this one, right? There we go. I can find the greatest lower bound, and that's the level that they intersect at. So I could say that these two objects are, let's go 0, 1, 2, 3. So these two objects at level 3 are 1 intersecting because their greatest lower bound has rank 1. And so I can take a lattice and I can look at the greatest lower bound, that's the level of intersecting. So I could take a level in my lattice and ask for the largest set of objects so that they're T intersecting, so that any two of them, when I do their greatest lower bound, it's at level T or above. And this was done, there's a paper by Suda who showed conditions on a semi-lattice that would make an EKR type theorem hold. And there's also a paper that I did with a couple other people where we proved that EKR type theorems hold on the weak Brouhat lattice. And that's the picture that I have here. This is the weak Brouhat lattice on permutations. And yeah. So that's another very general way of looking at this. We saw another relation last week with Sam Mattis's talk last week, where what he did is he defined a notion of oppositeness. So instead of defining intersection, you can define objects being very different or opposite, and then ask for the maximum set of objects in which no two have this oppositeness relation. So we could say two sets are opposite if they're disjoint. So we want to find the maximum set of objects so that no two are disjoint, so they'd be intersecting. The example we saw was with flags. So with flags, you have a series of vector spaces, one contained in the other, and then you can take two flags. And the oppositeness idea is that if the intersection between the different vector spaces is as big as possible, they're going to be opposite. And then you go looking for the largest set of flags where you don't have this relation. And so this was the paper that we saw last week. Okay, so there's lots of different general frameworks to ask this question. I was actually going to spend a little bit of time at looking at a couple of examples where people have spent a lot of effort looking for EKR theorems. And my favorite actually these days are permutations. So if we have a group and it acts on a set, we can always ask for the largest set of elements. So I want to look for a set F from G, largest set F of elements from G. So that if I pull out any two group elements from my set, there's going to be an element in the set the group acts on so that G and H map that element to the same spot. So I've got a group acting on a set, two permutations in the group, two elements in the group are going to be intersecting if there's some omega that they map to the same spot. So that's my idea of intersection. So anytime I have a group, any action, I can start asking for what's the largest set of intersecting objects under this action. Now, when I have an action, there's going to be an H, and it's the stabilizer of the action on the set, so that the action is equivalent to G acting on the cosets. So every action I can encode on an action on cosets. So for any group and any subgroup, I've got an action and I want to ask, what do we know in terms of EKR stuff? If two guys are intersecting, that means there's some coset that my G and H map to the same spot. So that means this thing is in H. So two elements are going to be intersecting. If I go one times the inverse of the other, that has to be conjugate to an element in H. So there's this nice group theory feeling stuff going on. So what's the largest set of elements so that any pair has the property that one times the inverse of the other is conjugate to an element in H. And so this is the EKR theorem for a group with an action. And one thing, we've defined intersection density. Now, if I take my group H, clearly it's going to have a property that anything in H times the inverse of something in H is going to be conjugate to an element in H. So for sure, when I'm asking what's the biggest set, the group H is going to work for sure. So we're guaranteed to be able to have a set of at least H. And the question is, can we do something bigger? So we've defined the intersection density to be the ratio between the largest that's possible to the size of H. So if the intersection density is 1, H is our biggest, and we say it has the EKR property. And if the intersection density can be bigger, then we've got something bigger than H that is still intersecting with the action. So there's a ton of stuff to do here, because anytime you've got a group and a subgroup, you can ask what's going on. So there's a lot of work, and there's a group in Slovenia who've written so many papers recently on this topic. I just listed 4 of them here, written by some subset of these authors. And one thing that's interesting is they looked at this. You hold on to the symmetric group, and you want to look at the action of the cosets on C3. So just the subgroup of order 3 generated by a 3 cycle. And then if you spend a little bit of time thinking about it, what we're looking for is the largest set of permutations, so that 1 times the inverse of the other is a 3 cycle. And you can just play around with your multiplication. You don't need to know anything else other than how to multiply permutations. And you'll quickly see that it's going to have to be a set that looks like this. It's going to be, you can have the identity, and then you can have 1, 2, 3, 1, 2, 4, 1, 2, n. And so this is the biggest set of intersecting permutations. So with this action for the C3. So the intersection density is the size of the biggest compared to the size of the cosets we're acting on, like the C3. So the intersection, this has n minus 2 plus 1, n minus 1 elements over the 3. So this has size n minus 1, this has size 3, and the ratio is the intersection density is this n minus 1 over 3. So you can do this one by hand without too much trouble. And it's interesting because this is actually a really, really big intersection density. So 1 is when you have an EKR type result, and this number is much, much bigger than 1. So it's very far from having an EKR property. So there's questions beyond just looking at a group and a subgroup. We can actually look at what intersection densities are even possible. And so work that I did with Pablo Spiga and my student Biddy Razafima Hatratra recently, we looked at this question, and we found that if the degree of your group is bigger than 2, the intersection density can't be any more than n over 3, and that the intersection density on a degree P group where P is prime has to be equal to 1. So we can also ask, what are all the possible intersection densities for a given degree? So if your degree is prime, your intersection density is going to be 1. What if you're the product of 2 primes? Or what if you're a power of 2? What sort of numbers are possible? And there are some papers. I'll just put this one by my student Biddy, but a lot of this is really open, and we don't know yet. Oh yeah, and I want to say a few more things about the permutations. So we're looking at a group and an action, but some people don't like that, right? Because I talk about a group and I talk about it like it's a group property, but it's really a property of the action. So can we turn this into a question about the actual group? So what we could do is hold on to our groups and ask about the intersection density for every group action. So I want to find groups. When I consider any group action, the intersection density is always going to be 1. So we've got EKR for every single possible action. And there's this paper where that's what they looked at. And I think one example of what they showed is if you're holding on to a nilpotent group, then it's going to have the EKR property for every single action. And another direction you could go, if this is not enough different directions, sometimes looking for the largest intersecting set can be tricky. You can narrow it down and just ask for subgroups. Instead of looking for intersecting sets, you're going to ask for intersecting subgroups. And I think that problem becomes a lot easier because the groups gives you a lot to work with. And so this paper here is recent that looked at that as well. Okay, so that's sort of the permutation question in a nutshell, but there's a ton of interesting stuff here. Another EKR type problem that has a lot of work behind it are co-cliques in a graph. So if you hold on to a graph and you want to look at the K co-cliques, so these are independent sets or sets of vertices with no edges. The K co-cliques means that they have K vertices in them. I want to find the maximum number of K co-cliques so that any two have a vertex in common. So I'm looking for the maximum intersecting set of co-cliques of size K in a given graph. And so every time you have a graph, you can ask this question. If the graph is the empty graph, it's just the normal EKR theorem. If the graph is a cycle, it's the EKR theorem for separated sets. So sets where you never have consecutive elements. The graph is called EKR if the maximum set of intersecting co-cliques are all co-cliques that contain a fixed vertex. So if they intersect canonically, so if they intersect canonically, meaning they all have a common vertex, if that's the largest set of intersecting co-cliques, we say it's EKR. And now here, things get hard right away. That when we're looking at sets or like permutations of a transitive group, it's easy to know what the size of your canonical intersecting co-cliques are. But if you're holding on to a graph, one of the things you have to answer is which vertex should I use if I want to get the biggest set of co-cliques that contain that vertex. So for a graph, how many co-cliques of size K contain a fixed vertex? And how do we decide which vertex is in the most co-cliques? There's lots and lots of different papers on this. And I think this paper here, I think Peter Borges' one, looks at the question as to which vertex you should use. People first assumed it should be a leaf, right? Something at the end, not a lot of edges. You can add a lot of stuff, a lot of elements to it and make co-cliques. But they actually found examples where the leaves aren't the biggest, where some internal vertex is the right thing to pick. And then they're like, oh my goodness, like, what do you do with that? This paper right here from 2005 is one of the earlier papers in this area, and they make a conjecture about the structure of the graph. There's some condition on the size of the maximal. The maximal co-cliques have a property, then they conjecture that the graph has the EKR property. And it's been open despite people working on it lots. There's this paper where they look at the question for the union of paths of length 2. So people don't typically get too worked up about a graph that's a union of paths of length 2, because you're like, that's a pretty simple graph. But even graphs that simple, asking whether or not it has the EKR properties, kind of tricksy. And of course, this one I put here because, you know, it's called Stars of Caterpillars and Lobsters. So of course, everybody wants to read that. So the caterpillar is a graph that has a path and a bunch of leaves. So they describe it as if you take your tree and you pull off all the leaves. If you have a path left over, what you're looking at is a caterpillar. So if you have a graph and you pull off all the leaves and what you have left over is a caterpillar, then what you started with was a lobster. So I'm not sure. I kind of think the second one should maybe be a butterfly, but I don't know if that's sort of creepy or not. Anyways, so this is a whole world. The conjecture that's in this paper, I think, is still very open and it's not clear. I don't know that there's consensus about whether or not the conjecture is true. And you can look at any graph or any family of graphs and ask this question. And I'm going to talk a little bit about one more example. This is sort of the example that has vexed people. I think Sebi and I have had conversations about this. If you start with a convex n-gon, so an n-sided object, you can do a triangulation by adding edges, and the edges can only touch at the vertices. They can't cross. And so here I have n is 6, and I have n is equal to 6. I have a bunch of triangulations. I say they're intersecting if they have a common triangle. So all of these have the triangle 1, 2, 6. So this little triangle at the end two of its edges on the outside of the polygon, and I have one edge that's as short as can be. Believe it or not, this has a name. It's called, of course, an ear. So if I take all the triangulations that contain an ear, what happens is that I'm sort of cutting off vertex 1, and what I'm left with is like, instead of an n gone, it's an n minus 1 gone, right? So all of the triangulations that have this ear are all the triangulations of one size smaller. So it's like beautiful, right? It really, this should be the right answer. But we don't know. We can't prove very much about this at all. It's a really nice example where there's this nice relation going on and it seems just right, but we can't prove what the largest family of intersecting triangulations are. Gil Kalai has written a little bit about this. I've put a link to a comment he made on Math Overflow that gives just a little more context for this question. Okay, so those are sort of like the EKR theorem and the different situations in where you can ask if their aversion holds. There's a bunch of related questions, like what's the largest set of intersecting objects that aren't contained in a canonical one? So they aren't contained in a system where everybody contains a common element. So this system right here is the one I put at the beginning. It's all the 3 sets that contain 1. So what I can do is add in the set 2, 3, 4. This is sort of like any set that doesn't contain 1. And then I throw away the ones that get wrapped, right? Yeah. So if I take all the sets that contain 1, add one set that doesn't contain 1, and throw away the ones that are no longer intersecting, that aren't intersecting with this new one, this gives me a set that's still intersecting, but it's no longer contained in a canonical one. And these are called Hilton-Milner theorems. Hilton-Milner proved that this construction will give you the largest intersecting set system that's not contained in a canonical one. And so anytime we have a question about whether or not an EKR theorem holds, we can ask if a Hilton-Milner if a Hilton-Milner type thing holds. And there's a paper that my student Biddy and some other people did, where they looked for Hilton-Milner type theorems in a group, and they proved that there's no Hilton-Milner version, no Hilton-Milner theorem for this particular situation, and used that to prove the EKR theorem. So it's sort of a nice application of using Hilton-Milner type stuff. We can also start looking at what are called stability results. So by the Hilton-Milner theorem, it says that this number, this size right here, that's the largest set system that's not canonical. So really it's not contained in a canonical set system. I could take this canonical one and throw one away and be like, haha, it's not canonical, but no one's going to care. It's contained in a canonical. We can make it the biggest. So if we have a set system that's bigger than the number in the Hilton-Milner, then it has to, all the elements have to contain a common element. So it has to be one of these contained in a canonical intersecting one. So one question we can ask is find a C, and you want it to be relatively, oh, maybe we want it large. Hang on, I think we want the number here to be the largest C. Largest, smallest? What we want is we want to have a lower bound that we say, if our C is bigger than this number, then all the elements have to contain a common element. Yes, we want it small, I had that right. Okay, so this is sort of, these are called stability results that say that up to a certain threshold, weird stuff can happen, but once your set is big, you have to be contained in a canonical one. There's some really great papers, the stability version of the Erdős Ko-Rado theorem. They describe it as stability versions of such theorems assert that if the size of the family is close to the maximum possible, then the family itself must be close to some maximal sized family. So what they're saying is if we're really big, we're either contained in a canonical one, or we're pretty close. There might be a couple little guys that are weird, but for the most part, everybody has a common element. And so this whole world of stability results is really interesting, and there's a lot of new papers coming out with really powerful results. And there's even more related questions. So we've been asking for what's the largest set that are intersecting, we can start asking for what's the largest with an additional property. We can ask that it's symmetric, meaning that the automorphism group on like the atoms and the objects is transitive on our intersecting family, or we can ask for regularity. So regularity means like each of our atoms occurs in equally many sets in our intersecting family. So when we have a canonically intersecting family, everybody has one and all the other elements occur equally often. So it's very far from being regular because there's one object that's in everybody. What if we want all the atoms occurring equally often? And so there's a couple papers here on looking for symmetric and another paper looking at regular intersecting families. Oh my goodness, there's lots of questions. Okay, so we're looking for intersecting. We can also look for the largest family avoiding certain types of intersection. And so the Erdős shows in 1975 asked for the largest collection of k-sets so that they never contain two elements that intersect in t-1. So they're forbidding a certain type of intersection. And there's a link here to Gil Klei's blog where you can get more information. But there's a couple of results where they look at similar things. So rather than looking for intersection being size this or above, looking to forbid certain types of intersection or only allowing certain types of intersection. So there's a whole world of different directions that you can go. So you can apply your intersection to any number of different objects, and we can look at all sorts of variations of the question of what's the largest intersecting. Okay, so I have way more slides than I'm going to get through. I was going to spend a little bit of time looking at some different methods of proving EKR type theorems. Now, the plan A, whenever you're holding onto an object and you're asking if it has the EKR property, the easiest thing to do is a really simple counting. So what I'm going to do is I'm going to have P1, number of objects that have one fixed atom, P2, the number of objects with two fixed atoms. And I'm going to hold on to a set. I'm going to say it's not canonical. So not everybody contains a common element. And I'm going to get an upper bound on the size of it. And I'm going to be really sloppy about it. So I'm going to have this guy is an object in A. So I've got A1, A2, up to AK. My whole set system is intersecting. So everybody in my set system has at least one of these guys. So I've got a pile of objects that have A1, a pile that have A2, blah, 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 and a pile that have AK. So my set system is not canonical. So whenever, okay, there we go. It's not canonical. So for every I, there's some object that doesn't have AI. So every object in my set system has one of AI to AK. So I can take my set system and put them in different piles. This first pile are all the guys that have one, all the guys that have two. Somewhere in here, there's a set that has no A1. Everybody in here has to intersect with this guy. So there's some element that has to be in both of them. This guy has K elements in it. So there's K choices for this. So all the guys in A1 have A1, some K guy from over here, and then the rest of it. So what I can say is that the size of my set system is no bigger than however many ways I can fill this in, the K, the number of ways that I could pick the one that needs to intersect, and then I had 1, 2, 3 K piles, and that's this K right here. So the size of the set system is bounded by K squared. How many ways can I complete an object once two atoms are fixed? So what I can say is that I'll have the EKR property if this bound is smaller than canonical. And this is super sloppy and really lazy, but it works in a surprising number of cases. So if we're holding on to uniform partitions, we've got the formula, we can work it out. Basically, it works. So uniform K partitions, so that's where I'm taking a base set and dividing it up into K cells, each of size L. If that L is bigger than 2, this works. If I'm holding on to designs, I can write down the formula and I get this bound. So my design N is the number of elements I'm taking, m is the size of the blocks. So if the size of the blocks has this bound, so my blocks are small compared to my end, this is going to work. But if I look at permutations, it's never going to work because the k and the n are tied together. The number of atoms in my object, my atoms are maps I to j, I'm going to have n of them. So I don't actually have two parameters, n and k, and I can't just drive up the n large relative to the k. So this is never going to work. Triangulations of a convex polygon, we have the same problem. It's never going to work. So it's sloppy, it's approximate, but it will give you an idea of what happens asymptotically without doing too much work. Left compression. The less said about left compression, I think is kind of the best. This was used in the original proof and the Osfeda-Ketchatrian proof. And I don't know that there's a proof of the complete EKR theorem without using the left compression. But the idea is that you have a set system and you want to change it so that your numbers are as far down in the your sets are as far down in the co-lex ordering as you can possibly get. And that gives you a little bit of structure. But the compression can be good and bad. Like the compression, it's been used in a bunch of cases. Talbot used it for separated sets. And he also used it with Borg and Holroyd to prove that Co-cliques in a specific family of graphs has the EKR property, which was pretty impressive. Ku and Wang used it for cycle intersecting permutations. But it can be really hard to make a compression that works. So there's an obvious compression that works for permutations and perfect matchings, but it's not one-to-one. So if you ignore the fact that your compression is not one-to-one, so that if you take a set and you compress it, you could get something smaller. If you ignore that little fact, we can basically get a version of Osfeda-Ketchatrians for permutations and perfect matchings, but it's still wrong. And there are published papers, one for vector spaces and one for permutations, claiming that the compression works when it doesn't. So that is a method that I would maybe advise against, unless you're very, very careful. What I think you should do is when you're looking at EKR theorems is to look at an object called a derangement graph. So what I do is I make the vertices be the objects that I'm considering, and I make them adjacent when they're not intersecting. And now I'm looking for a co-clique in a graph. And so for lots of examples, so sets, this derangement graph is the Kneser graph. Vector spaces, it's the Q-Kneser graph. For permutations, it's just called the derangement graph because when they're not intersecting, they're derangements. And often we use the term derangements for all sorts of different objects, not just permutations. So the question becomes, what's the maximum co-clique in the derangement graph? And so what we want are both the size, what's the size of the largest co-clique, and what are all the sets that meet this bound? Like what exactly are all the co-cliques? And putting this in terms of a graph opens up the world of graph theory to you, and you can use a lot of tools. So for example, we can use a graph homomorphism. So the picture I have right here is the derangement graph for the sets. So K52, so Peterson graph, which obviously you can't have a talk in this seminar without a picture of the Peterson graph. And this guy right here is the derangement graph for multisets. And so the derangement graph for the sets is a subgraph for the multisets, and the multisets just has a couple more edges thrown in. So the size of a co-clique in the multisets, it can't be any bigger than the derangement graph for the Peterson because we've just added more edges. And so we can do a homomorphism, or it's actually an embedding. And so I can give you a bound on the size of the co-cliques in this graph because all I've done is added more edges to a graph that I understand really, really well. So you can actually, this is something Allison and I did ages ago. You can prove an intersection theorem for multisets just by using this nice little homomorphism. So when you think of homomorphisms, you think of colorings and fractional colorings. So looking at fractional colorings, we get a nice bound when we're holding on to a vertex transitive graph. So if our graph is vertex transitive, alpha x, the size of your largest co-clique, omega x, the size of your largest clique, it's bounded by the number of vertices in your graph. And if you have equality, then every maximum co-clique and every maximum clique intersect in exactly one point. So a lot of our derangement graphs are vertex transitive because in a lot of the examples, not all, but a lot of them, the atoms are all exactly the same, and our objects, we can do an automorphism on the atoms that map that's transitive on the objects. Like if we're looking at length and integer sequences, we have a clique of size q. We just take all of the sequences that have all of the entries completely different. So go 0, 0, 0, 1, 1, 1, 2, 2, 2. That will form a clique in our derangement graph. If we're looking at perfect matchings, a 1 factorization is a clique. And if we're looking at permutations, a sharply 1 transitive set is a clique. So in all of these examples, we get the EKR property with very little work. And for permutations, this was done like in the 70s by Des M. Frankel. And recently, I guess 2008, a paper came out that basically used the second part of the clique, co-clique bound. They used this part that if equality holds, every maximum co-clique and clique intersect. And they're actually able to push that carefully to get the characterization to show not only the size of the largest co-clique, but the only largest co-cliques are the things that stabilize a point. Okay, so I was just going to stop briefly about, say something about when we're holding on to permutation groups. So if we have any subgroup of the symmetric group, so this is a group with an action, I can embed it in a permutation group. Gamma G is the derangement graph, and vertices are adjacent if one times the inverse of the other is derangement. So this is exactly group acting on a set. You can represent it as a permutation group, and then we make the derangement graph, and this is the condition for 2 vertices to be adjacent. So this is the derangement graph for the dihedral group. This graph is always going to be vertex transitive because the group acts on itself. A canonical co-clique is the stabilizer of a point. So long as we're transitive, I know exactly what size it is, and that's my candidate for being the largest intersecting. If I have a sharply 1 transitive set, so like I have right here, I've got an n cycle. I take the subgroup generated by that. That's going to give me a clique of size n. So if I have a sharply 1 transitive set, the clique co-clique bound tells me that this is the largest intersecting set. So for sure, I'm going to have the EKR property. This guy is also a normal Cayley graph. It's a Cayley graph because the vertices are elements of the group. The connection set means that 2 things are adjacent if 1 times the inverse of the other is in the connection set here. And it's also normal. Normal means that the connection set is closed under conjugation. So once we're holding on to a normal Cayley graph, we have a way of calculating the eigenvalues. We can get the eigenvalues from the irreducible representations of the group. Not only that, our derangement graph is a graph in an association scheme. Okay, so an association scheme, I won't go through the whole definition, but we have a bunch of matrices. One of them is the identity, all of them are 0, 1. They add up to the all ones, and they have this magic property that the matrices as I hold them are linearly independent and make a vector space. But if I start multiplying them, I only get things that are linear combinations of what I started with. So when I go from the vector space to the algebra, I don't get anything new. So this is sort of like a magic property. This is like what's really important going on here. Basically, we have the algebra generated by the matrices is really super nice. It's called the Bose-Mesner algebra, and we can do a lot with it. Yeah, let's just leave it like that. We've got a really great algebra sitting here. With lots of cases, when we have an EKR theorem, the association scheme is something we know really well. When we're looking at K sets of an N set, it's the Johnson scheme. K-dimensional subspaces, we're looking at the Grassmann scheme. And for the case of the permutations, what we're holding on to is the conjugacy class scheme. And in these cases, the adjacency matrix of the derangement graph, it's going to be a sum of matrices in our association scheme. So what we can use are the Delsart-Hoffman bound. So a weighted adjacency matrix of a graph, it's going to be a symmetric matrix. The rows and columns are indexed by the vertices in our graph. And the entry, the VW entry is 0 if they're not adjacent. And if they are adjacent, it can be whatever you want. What you picture is taking your graph and putting a weighting on your edges, and then the matrix records the weighting on the edges. Now, if I'm holding on to a weighted adjacency matrix for a graph, and I have constant row sum D and least eigenvalue tau, I can get a bound on the size of my co-clique. And the bound is number of vertices divided by this. My D is going to be, the row sum is going to be positive, the tau is going to be negative. So this whole thing is going to be a positive number. What I want to do is find a weighted adjacency matrix that maximizes this, and that will give me the best bound I could get. Now, if I have equality, I get the second part, that if equality holds and I'm holding on to a maximum co-clique, the characteristic vector minus a multiple of the all ones is going to be an eigenvector. And Hammer's put out a paper on the archive that gives a lot of detail and history about the ratio bound. It's a really nice paper that's worth looking up to someone who knows the history well. It's lovely. Okay, so in a lot of these cases, if I'm holding on to an association scheme and my adjacency matrix is a sum of graphs, matrices in my association scheme, what I can do is to find my weighted adjacency matrix is I put weightings and I keep them constant on the matrices that are in the association scheme. So the adjacency matrix for my graph is the sum of matrices in my association scheme, and I can get a weighted adjacency matrix by weighting the matrices in the scheme. And what I want to do is find a weighting so the ratio bound gives me the greatest ratio between the degree and the least eigenvalue. And hopefully, if I'm lucky, the ratio bound will work with equality. This is what Wilson did. And then Wilson and Frankel did it in a couple years later for the k-dimensional subspaces of a T-space. Whenever we have a clique and there's equality in the clique co-clique bound, a weighted adjacency matrix that will give us the right number in the ratio bound is going to exist. And this is something that I did in a paper a little while ago. There's also this interesting paper by Chris and Crystal that sort of used this idea that they were able to prove that a weighted adjacency matrix would always exist. This paper builds on Wilson's paper because Wilson wrote down the matrix and was like, ta-da, look at the matrix, it works. And you're looking at it and like, wow, it does work, that's amazing. Chris and Crystal sort of help explain why it works. Okay, so there are many cases of when the ratio bound holds with equality. Looking at perfect matchings when T is equal to 1 and 2, looking at permutations, and there's references here, looking at graphs that are graphs on a vertex set that intersect in a triangle, you can make a ratio bound version work as well. I'm trying to go quick because I see my time is rapidly running out. I don't want to stress Tina out. One thing that's really funny is that for two transitive groups, this works really, really, really well. When you're looking at two transitive groups, we can calculate the eigenvalues from the irreducible representations. When we're two transitive, we have a character that works perfectly, gives us exactly the right number that we want. And for many two transitive groups, this approach will work to show that they have EKR property. Some other two transitive groups, we have to use a weighted adjacency matrix, but they're actually really simple weighted adjacency matrices work. And what you can do is whenever your group is two transitive, it's going to have the EKR property. And it's essentially this ratio bound just seems to work over and over. Now, one problem with the proof is we have to apply it to each group carefully. There's no proof that says if you're two transitive, like without looking at each group separately, we can't prove it. Okay. Maybe I'll just end mentioning the EKR module property. This is sort of a newer property that people are looking at. One of the things about the ratio bound is it says if you have equality in the ratio bound, then you take your characteristic vector of the largest co-clique and subtract off on all ones. That's going to be a tau eigenvector. So it's going to be an eigenvector. In many cases, we can show that we can hold on to this eigenspace, and we can show that the characteristic vectors of the canonical intersecting set span this. So what happens is that the characteristic vector of any maximum intersecting set is a linear combination of the canonical ones. So when this happens, I'm defining it roughly, but this is essentially the idea of the module property. So we say our set has the EKR module property if the characteristic vector of any maximum one is a linear combination of the canonical ones. All two transitive groups have this module property. And there's a nice paper that Nathan Newville put out recently that uses this property to show how you can get the characterization. So for lots of groups, this property is used to show the characterization, and they push this just a little bit further, and they have a nice paper that's worth checking out. Okay, low degree Boolean functions, totally something I should talk about. It's like really great. There's all these good papers. So here are some references. Probabilistic methods are totally a thing, and they're really useful. There's a couple references here. There's this new paper that I think is really interesting, but I guess it should get you excited. Be like, oh, probability, we can use that. And I've got a few last related problems. We're looking for the largest co-clique in a graph. What about the largest bipartite subgraph? What about the largest triangle-free subgraph? What are objects that do not have the EKR property? Like, is there something natural that looks good, but it really, really doesn't have EKR property? And what's going on with that? And what about some general theorems? Like, it's fine enough to like write this laundry list of objects that have the EKR theorem, but wouldn't it be nicer to have like, if your object has a two transitive automorphism group, then you have the EKR property. Like, that's a much more exciting direction, I think. Okay, I'm sorry, I feel like I've gone way over. Tina's probably like, mute.
Yeah. Okay. Thank you, Karen, for a very nice and thorough talk about Erdős Ko-Rado theorems. So let's thank Karen. Okay, so is there any question for Karen? Yes, Peter.
Good. May I make a couple of remarks? One is Karen mentioned that the first EKR type problem for graphs for Holroyd and others, while Szymonovich and Verashos wrote a series of papers in the early 80s about the question that you are given a graph and you want to find a bunch of triangles which share, every pair of the triangles share an edge. What is a possible configuration, such as things? And they find properties where it proved to be Erdős Ko-Rado type property. So the best way was picking up an edge and all triangles sitting on this edge. This is one thing what I would like to mention. The other thing is Karen mentioned that the shifting method in the Algebraic they didn't use the left compression. They used another compression called middle compression. They compress the system at first to the left, then to back, and this is how they get the result. It's a very complicated method. And third thing that I would like to mention, that she told that there are not too many extremal systems where the left compression work. One, for example, if you are considering intersecting chains of subsets. So you are given the Boolean set. You are looking for chains, bigger and bigger and bigger and bigger sets sequence, and two chains intersect if they contain a common subsystem. And for this system, the Erdős Ko-Rado property true, and it was proved by left shift method or left compression method. However, the Hilton-Milner property was proved for the same system with Kernel method. So for that one, the shifting method, that it did not work. This is not the Erdős Sós, this is Simonovic Sós, but this is a different thing, what I mentioned at the beginning. And the fourth thing that I would like to mention is, I don't know how much is known, but Erdős Ko-Rado theorem gave a way to prove reconstruction type result for hypergraphs. It is called Berge and Fournier result, and was a generalization of Lovász. You can find in the Lovász book. And this is something like you pick up the whole K-uniform hypergraph. You take a permutation of the edges so that any two intersecting edge goes to intersecting edges. And the statement is that if you do that, then you have to find, you can find a permutation on the vertices, that this permutation map the vertices to each other, and all edges go by the images of the permutation. And you can prove this result and a lot of similar results using Erdős Ko-Rado theorem.
Yeah.
I think that's all. Thank you.
Nice, thank you. I appreciate that, Peter.
So any other question for Karen?
So I just want to make a quick comment. So first, thank you, Karen, for a wonderful talk and wonderful book and papers on this subject. It's fascinating that the same results can be proved by so many different methods. And kind of here, it's like the gathering of more algebraic part of the community. And I just wanted to mention that the Co-clique conjecture, that's an example where the algebraic method doesn't seem to work anymore. So like Karen tried and other people, if you construct this this graph kind of similar to the Kneser graph on the Catalan on the triangulations, and you try to do this graph, then this graph is not even regular for n greater or equal to 7. And so you can try to apply some eigenvalue bounds and so on. They're not that sharp when the graphs are not regular. So there's definitely need for like new tools or methods. And one thing that was interesting is that we did some calculation with, well, mostly Christine Bachok did the calculations a few years ago. And it turns out that for these graphs, if you take the floor of the Lovász theta function, which is the upper bound for the independence number, it meets it gives you the it's tight for n up to 10 or something like that, and then it becomes difficult. So that's kind of intriguing, fascinating, but yeah, so kind of shows there's a lot more to be done in this area. Thank you.
Yeah, thanks for that, Sebi. I think the triangulations are very interesting. Am I right in saying they sit in a coherent configuration as opposed to an association scheme?
I don't know that. I don't know.